Okay, ladies and gentlemen, I will present you an engineering approach to fatigue analysis based on elastic plastic fracture mechanics. In my presentation I will talk about fatigue testing, about the stages of fatigue crack growth. I will present an approach to fatigue analysis considering the transient crack opening behavior. I will present you the numerical analysis I have done and the determined analytical solutions, and I talk about the selected fatigue crack growth parameters and the application of the approach. We have done strain controlled fatigue tests with an ferritic ductile cast iron with axial tension compression loading on unnotched round specimen having a machine specimen surface. The material exhibits cyclic strain hardening in a known manner, and as you can see on the figure on the right hand side, the elastic plastic material on the cyclic loading can be well described by the Rambert-Bosscoat equation. In the presented approach, I have considered the material is cyclic stabilized. We have also done fractographic examination to find the cause of failure, and we have found microporosities from 60 up to 500 microns. And as you can see in the figure at the right side, I have modeled the defect as a semicircular surface crack with an initial crack depth according to Murakami's square area criterion. In industrial application, often the crack initiation of technical size is interesting, and if there exist defects and or higher loadings, this period is dominated by the growth of mechanically short fatigue cracks. And as a result, I have concentrated in my work to modeling the mechanically short fatigue crack growth. But what has to be considered? The conditions of small-scale yielding are not fulfilled during the growth of mechanically short fatigue cracks and or higher loading. The application of conventional approaches of linear elastic fracture mechanics might be no more adequate and might lead to non-conservative results in fatigue life assessment. Furthermore, the cracks grow only in open stages, and on the elastic plastic loading, crack opening and closure can occur at stresses differ from zero. Furthermore, the crack opening stresses develop in a transient process up to the stabilized level for long cracks. Here you can see an overview of the presented approach. I've considered the elastic plastic material behavior and the transient crack opening behavior. I've used analytical solutions to calculate the effective change current range and describing the crack growth with the Paris crack rollers during the effective change current range. Afterwards, I explain it in detail. As you can see in the figure, there are experimental data of a ferritic cast iron taken from a publication of Mr. Clement. You can see the transient crack opening behavior of short crack, and the transient crack opening behavior can be well described by a model of Professor McAvely. Following that, I've used in the approach McAvely's model to calculate the transient crack opening stresses from a fully opened crack up to the stabilized crack opening stress calculated with the widely used formula by Professor Newman. I have done further assumption in the approach. First one, Newman's formula is suitable for higher maximum loading and a stress ratio -1. The flow stress in Newman's formula is calculated with an equation by Professor Formel, and based on experimental studies by Professor Formold, I assumed identical crack opening and crack closure strength in the approach. In the figure, you can see that I use the effective stresses and strain and the transient crack opening behavior from the lower level up to a stabilized level calculated with the formula by Professor Newman. I've also done numerical analysis, three-dimensional elastic and elastic finite element analysis of a round bar with a short surface crack to get the J integral values. In fatigue crack curve analysis, I have to approximate the J values with analytical solution. On one hand, I have used the well-known Dowling's formula for short semicircular surface cracks, and on the other hand, I have determined an analytical solution based on the reference stress approach, using, for example, the R6 procedure, and a modified procedure according to Professor Zerbst. In this modified procedure, the reference loads are derived from J integral values calculated by the numerical analysis and setting the ligament gilding parameter to 1. The effective J integral range was calculated comparative on the one hand with the Dowling's formula modified by Professor Formold and by taking into consideration the transient crack closure behavior, and on the other hand I have used the determined analytical solution based on the reference stress approach and also by taking into account the transient crack closure behavior. To determine the parameters C and M for the crack growth, I have used the cyclic crack growth data of a ferritic ductile iron taken from a publication of Professor Hübner. The test was done according with the ASTM guideline, and there is a good approximation using the NASGR equation and following a good approximation of the stress ratio effect using Newman's crack opening stress formula. Further experimental studies demonstrate a good correlation of the crack growth data of mechanically short cracks with a long crack growth data determined at high stresses ratio for cast iron materials, and so I can determine the parameters C and M for the crack growth using the effective J integral line considering the cyclic crack growth data that were published here. As a result of comparison of the calculated and the experimental determined cycles to initiate a crack of technical size for the mentioned ferritic ductile cast iron, the calculated number of cycles differs by no more than a factor of 2.4. The analytical solutions based on the reference stress approach tends to be more conservative. For a conclusion, drawing on the given example, the application of the presented approach is successfully demonstrated to analyze the experimental fatigue testing results. And I want to sum up my presentation. I have present you an engineering approach to fatigue analysis based on the elastic plastic fracture mechanics. I have described the process and boundary conditions, the initial crack model of the defect, the elastic plastic material behavior, how I have considered the transient and the stabilized crack opening and closure behavior. I have shown you the used analytical solutions to calculate the crack tip loading and show you the selected fatigue crack growth parameter. To sum up, the application of the approaches based on mechanically short crack growth is successfully demonstrated to analyze the experimental data. So thank you very much for your attention.
Thank you very much. It all works, so I guess there are no questions. Can I maybe just explore first what is the kind of the practical application of this, because you started by talking about a material which has naturally occurring defects, Murakami square root area values 500 microns down to, I don't know, 50 microns or something like that. So would the application be that you know, you have a problem and you want to know, is it a good idea to reduce the defect size? Because these are defects you can't detect by NDT, right? So I guess you could say to the manufacturer, maybe you have to improve your manufacturing process to reduce defect size. Is it worth doing? I mean, would that be the kind of practical application?
That could be a practical application. On the other side, if you have to do a fatigue life assessment using the strain life assessment, you will use some strain life data, but this data have always scatter, and the scatter is, or the defects are responsible for the scatter.
Okay.
And so you can, with this approach, you can do calculate, or you can calculate the source of the scatter, and to make an assessment of what you need for the casting quality in your component.
So can you tell us that there is some defect size, and if we are less than that, it doesn't affect the fatigue life anymore? Yeah, there must be some cutoff value.
If you have enough low loading, I think it's possible, but if you have, it's a combination of the loading situation and the defect size, I think so.
But you know what? I guess what the manufacturer wants to know is, I mean, they can never make a component with no defects, so they want to know if it's less than 100 microns, I'm okay. I mean, I would say for cast iron, if it's less than a millimeter, you don't have to worry anyway, you know, because it won't actually change the life compared to a perfect piece of material. You know, typically. So, you think there's some kind of limit there you can tell as well?
I can't tell you a limit, but I think it's depending on the loading situation. If you have a hotspot with high loading, you have to get with a high loading situation, you have to get a very good quality for casting. But if you have not a hotspot, but you have a defect, a big defect in it, it could be a hotspot because it has a big defect inside.
Creates its own stress. Okay, anyway, probably some more questions there, yes.
It's very interesting to have so good correlation with the last. But the question is, for defects, play a role not only shape, size, but state at the T, because it will be difference in stress concentration. That's why it will be difference in track initiation, propagation, first of all, because it can be in that direction, first of all, it will be different in shapes and so on, it will be difference in prediction. What about this?
You mean that if you have
because you would have, the same area,
yeah,
but with the difference in stress concentration by the
shape of the defect. But of course Murakami will tell you, no, it doesn't matter. It's,
no. It was considered, for instance, by Barretta with Murakami for different type of faults, for instance, cast faults. It was principal difference in estimation, because there should be used difference in factors that estimate this in terms of difference in stress concentration.
What do you think? You assume it's a crack, but it's not really a crack.
That it's very deep knowledge should be used, not only about.
I think you're right. There is an effect of the shape.
Yeah.
But if you see many fractographic examinations, you can see very complexity of microporosities, and it's not easy to
Yes.
describe this shape. You have to approximate it in a way, and this is one way I have to do, but you are right, the shape isn't parameter at all.
For instance, we had a problem with a different kind of material, but the problem was pores which were spherical, you know, very close to spherical. And what we found was there were quite a lot of pores, and the actual failure always occurred when you had two pores which were close together, and so then they made another pore with a different shape, and this had a bigger stress concentration factor. So sometimes you can, okay, you can't model them exactly, but you can make models which include kind of typical pore shapes, I suppose, and see with them.
If you have when you have an advantage if you have gas pores, because they are round, but micro shrinking pores, they are very complex in the shape.
Yeah, and so probably they are close enough to being cracks. In fact, they're always somewhere there is a sharp corner there or something.
And also interaction effect between materials, because grain size and shape of the tip of this faults will be also big influence, because it's interaction effect because of not only stress concentration but material possibility to relax this influence on strain factor.
But
because of grain size will also influence.
It's more important in the high cycle fatigue area near delta K threshold, and in the low cycle fatigue you are on the Paris degree, and so you have not so an influence of the microstructure.
Thank you.
Any more questions? Yes.
In your comparison, you have always compared samples with different. You have you have for each sample you have determined the size of the defect and then estimated the lifetime, or these are different low plastic strain amplitudes.
Yeah, there you see it's from 1,000 up to 200,000, and you have different level of strain amplitudes.
And you have assumed for all the same defect size?
No.
Always you have controlled the defect size?
I have always done this spectrographic examination for every specimens, and take this get from this.
And then I really understood how you have calculated the effective plastic amplitude, but with the elastic, I think I'm not sure if understood not the elastic part. You have only closure in the tension region, but for the plastic part, you have taken the whole amplitude. That's somewhat strange to me.
Yeah, and the elastic part, or you have take this one?
Yes, here you have taken the elastic part from the McEverly estimation, yes.
Yeah.
And in the plastic case, you have taken
this. This is the plastic strain amplitude, but I've used also the closure.
The closure from the. Okay, so these are consistent.
That's consistent.
It's consistent, but I should see slightly different ways. Yes, we can discuss it.
So, just well, we have a little time. If anyone has a question, either for the speaker or for any of the speakers, any more worries about plasticity and ratcheting, now's your chance to ask. Maybe you're thinking ahead towards lunch, but it's 15 minutes before they open the door to the dining room. So. Okay, I think we'll let you go there. Thank you very much.